We continue our discussion on evaluation of limits by looking at a problem which will involve factoring and canceling. So we have the limit as x approaches 3 of x cubed minus x squared minus 6x over x squared minus 4x plus 3. And because if we plugged in x equals 3 directly, we'll end up with a 0 over 0 situation. So next step, we try to simplify this expression by factoring. So if we factor out an x at the top, we have x squared minus x minus 6. If we can try to factor the bottom as well, we'll have x minus 3, x minus 1. And we can continue trying to factor this expression, limit expression, until we have something that likely be able to cancel. So this has x squared minus x minus 6 can be factored into x minus 3, x plus 2. And then that will be all over x minus 3, x minus 1. Notice there's a common factor in both the top and the bottom. So now this will become a limit. X tends to 3, x times x plus 2 all over x minus 1. And then let's see if we can plug in at this stage and see if it works out. So 3 times 3 plus 2, that'd be 3 times 5. And 3 minus 1, that would be 2. So final answer is 15 over 2. And we're done. The next problem again involves the division by 0. So we'll have to try to simplify that. And in the way that we will try to simplify this expression is by noting that the expression at the top, which is radical 2h plus 13 minus radical 13, we can try to multiply by its conjugate, or what some writers call rationalizing the numerator, to get a simpler expression. So that's radical 2h for 13. And then instead of a minus here, we put a plus, radical 13. That is the conjugate. And recall earlier on when you met conjugates, you notice that when you multiply conjugates, you get a difference of squares automatically. And if you want to show that maybe in a longer way, you can just FOIL out the terms, and you'll find that at the end you end up with the first item squared minus the second term squared. Right, so that would be 2h plus 13. That's the square of this first term. And then minus square of the second term, which is minus radical 13 square, which is a 13. And then this will be h times radical 2h plus 13, and then plus radical 13. And then let's continue simplifying this. All over is 2h plus 13, then minus 13. That's just going to leave us with 2h at the top, and then h at the bottom. Radical 2h plus 13, and then plus a radical 13, and then we're almost there. We can cancel out the h's now, live with 2 over square root 2h plus 13 and then plus radical 13 here. But h will tend to 0 here, so h equals, so you can plug in h equals 0. So then you're left with, so we plug in h equals 0, and so you're left with 2 over 2 radical 13. And your final answer, most simplified, will be 1 over radical 13. And we're done. Alright? Okay. Again, remember, when we have limit expressions or problems with limits to solve, the first thing that you might try to want to do is to plug in directly. If it doesn't work, or if you have a division by 0, if you have a 0 divided by 0, something like that, then we try to simplify the expression. We can use factoring and canceling. We can use rationalizing the denominator. If you have a bunch of fractions, you can probably try to add them, like a bunch of rational expressions with fractions. Try to simplify it as much as possible using the algebra that you know before, at the end, you try to plug in the value, the numerical value of the variable that you want to work with. All right, that about completes evaluating. The other thing that we want to learn about in this section is something called the Squeeze Theorem. And Squeeze Theorem involves working with at least 3 functions. 2 of these functions are on opposite ends of the middle function that you want to work with. Really, one is higher and one is lower, and both of them must have the same limit or the same limit value at the point where we want to evaluate the middle function. Okay, so it says suppose that all x on an interval, closed interval AB, except possibly at x equals c, we have 3 functions: f of x, which is less than or equal to h of x, is less than or equal to g of x. Suppose that the limit as x approaches c of f of x is equal to the limit as y approaches c, that should be x approaches c, of g of x equals L. So the limit of the upper function is equal to L. The limit of the lower function is equal to L for some a less than c less than or equal to b. So a less than or equal to c. So in this interval, the point c that we're interested in is within the closed interval. Then, since the upper and the lower functions, f of x and g of x, the limit of those functions is equal to L, then the limit of the middle function, h of x, will also be equal to L. The limit as x approaches c, which is the point that we're interested in, the x value that we're interested in, will also be equal to L. Okay, and here's a nice visual diagram for you to figure that. Notice the g of x function is above the h of x function, and that is above the f of x function. And what these two, the upper and the lower functions, as they approach this x value c, they are the same value, L. And if the h of x function is between these g of x and f of x function, then these two functions will likely squeeze the h of x function up right there to being the same limiting value. So, without being able to calculate exactly the limit as x approaches c of the h of x function, because we know what g of x is approaching and f of x is approaching, then because we know that if the h of x was between these, then the limit of the h of x function will also be the exact same value. So let's look at an example. Find the limit as x approaches 0 of x squared cosine 1 over x using the Squeeze theorem. Now recall the cosine function oscillates between -1 and 1. So if you remember what the cosine function looks like, was -1 and 1, positive 1. Okay? Now, we can write that -1 less than or equal to cosine of x less than or equal to 1. Our function, we want to find the cosine of 1 over x. Right? We know that if x equals 0, that will blow up the 1 over x function, but we're not really interested in where it blows up. We're just interested in what is happening as it approaches. Right? So we can avoid x equals 0 altogether and just look at what is happening to the cosine function itself. So we do not need to input x equals 0, again, because we're only interested in limits, right? So -1 is less than or equal to cosine of 1 over x less than or equal to 1. It is true that the cosine function of any input will always be between -1 and 1. But we want x squared times a cosine of 1 over x. So if we multiply through everything by x squared, we'll have -x squared is less than or equal to x squared cosine 1 over x less than or equal to x squared. And then what we can do next is to find the limits of the outside functions right here, the -x squared and the x squared. And if the limits of these two functions as x approaching 0 are equal, then we know that the limit as x approaches 0 of this middle function x squared cosine 1 over x will also be equal to the same value. So let us try to find the limit as x approaches 0 of x squared and the limit as x approaches 0 of -x squared. What is the limit as x approaches 0 of x squared? That would be 0. But as the limit as x approaches 0 of -x squared, that is also 0. So because the limit as x approaches x squared, as x approaches 0 rather, of x squared is equal to 0, and the limit as x approaches 0 of -x squared is equal to 0, and because the function x squared cosine of 1 over x is between those two functions, then we can say the limit as x approaches 0 of x squared cosine 1 over x is equal to 0 by the Squeeze theorem, and we are done. Thank you very much for watching.